Now, we will look at that another application of homomorphic processing, that is homomorphic deconvolution. Sometimes the situation is even more complex. The two signals which we are calling that they are interfering with each other, one is of signal of interest, another that is what we name as noise, they are actually getting convolved with each other. Now, convolution means it makes it even more difficult to separate them out, but we can make use of the homomorphic filtering to take care of them, or in other words to separate them, to get rid of the interference. Okay. So, here let us look at that example that of homomorphic deconvolution. In this case, say the input signal or the observed signal x n, it is actually consists of the two parts again x 1 and x 2, but they are actually convolving with each other. Okay. So, we have actually that one of them we can say that the signal, another is that filter impulse response, there are two signals, they are getting convolved with each other, that is the way they are we are getting them. Okay. And one of them x 1 or x 2 is of interest depending on that what we are looking at, but unfortunately we get it in them in such a complex form, and we cannot, because they are not additively combined, we cannot use the direct linear filter, they are not multiplicatively combined, we cannot use the previous technique. So, we need to look for a different way to take care of them. That in this convolution in time, actually that what we can do to take care of it, we can think of taking them in the frequency domain. In the frequency domain, we know the signals which are in the time domain related by convolution, they become actually product of each other. Okay. Now, using that fact that multiplication in the frequency domain, in fact, now we are comfortable, we know, because that if the two constituents they are actually combined in a multiplicative way, we already know that how to separate them out. Okay. So, only thing the operation becomes a little longer. Okay. So, here first then to separate these multiplicative components, what we need to do, we need to take complex log, and out of the complex quantity x n, if we have taken the log, then we could actually separate that real and the imaginary part of it, that the real part would be the log of the absolute value or the mod, and the imaginary part would be the complex angle, and then we need to take also the complex exponential in this that total game, because we need to come back to the original domain. So, we need to cancel the effect of complex log, and if we take actually the complex exponential of the complex log of the quantity, we can get back the same output. Okay. And now, we look at the overall system. First, we take the Fourier transform of x n, that is our the time domain signal, and that the operation here before the transform, it was convolution. Okay. The operator is given in there the left hand side. After the Fourier transform, the multiplication changes to the convolution changes to multiplication. Okay. The constituents are now combined with the multiplicative operator. So, after taking the Fourier transform, we get rid of the convolution operator and we get the two constituents or multiple constituents, they would be actually the multiplicative components. Now, to remove the multiplicative operator, we take the logarithmic transform or complex logarithm, and that gives us the form that where the components would be combined with the addition operator. Okay. Now, after getting that, it seems that we are just there, but we need to do one more operation, that initial data was in the time domain, and just because that our log operator works on the works better, that we need to get it before that taking the logarithm, that the constituent should be multiplicatively combined, we have to take the Fourier transform. So, we have gone already in the frequency domain. So, to do the linear transform in the time domain, we need to come back to the time domain again. So, we need to take an inverse Fourier transform, okay, and then we get something called x hat n, and these can be passed through a linear filter, and we can get y n provided these components they are well separated, okay, that they can be separated in that way. And after that again we need to get rid of the effect of the logarithm what we have taken, and as the logarithm has been taken, after the Fourier transform we need to follow the same set of operations. We need to first take the Fourier transform, then take the exponential transform, that complex exponential, to get rid of the effect of the logarithm transform, and because we have taken the Fourier transform, to nullify the effect of it, we need to take the inverse Fourier transform, and again we see that operators keeps on changing. We started with that addition initially before the Fourier transform. After the Fourier transform, because it is a linear operator, we had that addition operation. Now, after taking the complex exponential, it becomes multiplication, okay, and that multiplication after the inverse Fourier transform, it becomes convolution. So, we get back to the original domain here, and we get the output as y n. Okay. So, that is the way we can actually have that the deconvolution using the homomorphic processing, and we can actually separate two components which are actually combined through that convolution operator. Now, let us take an example where actually such kind of thing is important. Okay. Let us take that we have some speech signal. Now, when we utter the vowels, that is called the voiced part of the speech, that the signal comes from the glottis, that is called the glottal pulse. It gives a repetitive kind of wave or sound, which actually gets convolved with the transfer function of our vocal tract, that from that glottis to our lip, that part, that there is a cavity, and if we think of a pipe in between these 2 points, that the shape of the pipe is not uniform. Okay. The cross section changes everywhere, and we also modulate that at a different way to make different kind of sounds, and because of the change in cross section, that it gets convolved with that actually the transfer function of the vocal tract, and the ultimately a voiced sound comes. And we know that what are the common voice sounds that we make, or the vowels we utter. In English they are A, E, I, O, U. So, in each of these cases we have the voice sound that comes out of our that mouth. Now, if we want to separate the two things, one is the glottal pulse and another is the vocal tract, that they are actually convolved with each other and we need to take the help of this homomorphic deconvolution. Now, before that, first try to understand that why we would be interested in such kind of activity. There could be many applications which will need only one component of them. You see that when we are uttering a sound, there are two parts. One part is specific to the person who is uttering that. If we are interested in that biometric identification, that means we want to identify that person with the help of the voice, that what that person is uttering, that means whether he is uttering A or E or U or some other word, that is not important. We want to know that what is the actually person is there and we would try to get that from the vocal tract, okay? Because just like our retina or thumbprint, that the configuration of the vocal tract or that cross section is also unique for each person. Okay. So, from there we would try to identify that person, and there that the glottal pulse, which is determining that what kind of sound we are making, that is actually becoming irrelevant. Okay. On the other hand, there could be some other application where we are trying to have a voice activated device. In that case, those parts which are actually personalized, that actually is causing a problem for the detection or taking that command. In fact, that is a nuance. The person which is the sound, the part of the sound which is specific to a particular person, it is actually is unwanted component. We are more interested that what is the command given. The command could be on, it could be off for a device, or we may say play, or we can say next, we may say previous to change the channels. So, those kind of thing we want that any person may be uttering those sounds, we should be able to capture that, identify that, and for that purpose it is best that if we can rub off those parts which are specific to a particular person and take that which is common for all and take it forward for that understanding that what is the command. Okay. So, such applications are there, that both the components are important, but in different cases. So, now let us take that how we proceed here in this particular case. So, first we take the Fourier transform and after the Fourier transform, the signal what we get, the voice pitch of that y f, that we get the two components x f and h f, and once we take the complex log, that we get the two parts separated, that log of x f and log of h f. So, we write them in a compact form, that y hat f equal to x at f plus h at f. Okay. Now, comes that fact of phase unwrapping. Now, let us try to understand that what happens, that is, as we told, that there is a actually that if we look at the one side is the frequency and the phase plot, that we know that there is some kind of continuity of it. Okay. Say there is a continuous change in the phase, this is the phase say phi, and say here it is 0 and here it is 2 pi. Now, after taking the log, what will happen from here, that once it goes to 2 pi means the same as the point 0, we will see it will look like this, that it will again build up like this. So, the trajectory will look like it is coming like from here to here and then going here. So, here is a jump of 2 pi, okay, which gives a discontinuity, and in some cases actually the discontinuities in the phase is not that actually important. For example, when we actually listen to the sound, that phase has little actually or less importance, though it gives some kind of artificial actually sound that effect, but usually that if we change the phase of, say, if we actually we can do an experiment that we can hammer a fork and get a frequency out of it. Now, if we do it at different time, we will see that it is giving the same sound. We are unable to get that what phase it is starting. That could be a simple actually test to get convinced that our ears are less sensitive to the phase. Okay. So, such kind of applications you can forget about the phase, but there are other applications like if we take an image, if you take the Fourier transform of it and you modify the phase, okay, you take the phase part of the Fourier transform of another image and then you go back again to the that original domain by taking the inverse Fourier transform, you will find that image has totally changed. In fact, the phase has more actually important clues in the visual system. In fact, that image from where you have taken the phase part of it, this image will look like more like that rather than that which has donated the intensity component. So, in such case you cannot ignore the phase and you need to restore the phase. The simple way that can be done, that what we need to do, we need to follow that for each frequency how much is the change in the phase. When the phase actually due to this complex transform there is a jump is occurring, the value of the jump is about 2 pi, right. So, we know it is a huge jump. So, when such a big jump occurs, then we simply add 2 pi and we put it back in the real place. So, that is called phase unwrapping, and after that we follow the rest of the operation. The main intention is to get back that phase in a proper way, that means removing the discontinuity, and that way we restore that the phase, and after the phase unwrapping we can do the inverse Fourier transform and we get back the signal that which actually is given as y hat, that is sum of x hat and h hat n. And here however, we need to keep in mind that n we cannot say same as the original that n, okay, that here we take a term called that it is called Q frequency. Actually we are changing the word frequency, jumbling that word and getting this new term, and that the new name is given for that the new signal, that is called complex spectrum. Again you get that spectrum part is coming from jumbling the word spectrum. Okay. So, this complex spectrum, why we are telling it in that way, because it has gone through some transforms and it is not same as the original the domain, that the time domain, because we have though that Fourier transform, inverse Fourier transform is taken, in between some log was also taken which makes it different, and this complex spectrum it has some good actually properties. If the original signal is real, which would be the case for the biomedical signal, the complex spectrum it is also real. Okay. That is one of the property that makes the life simple in many cases. For example, that we will see that later, that how that can help us. So, here we take the sound sample, and the first thing is to window that sample. The reason is that first we need to ensure the signal is stationary. The signal in real life is not stationary. So, we take the other definition of stationarity. We check for the weak sense stationarity, that means only the first two moments they would be constant over the time. In fact, that condition is also violated in practice, especially for the speech signal. So, we go for again a more loose definition, that is, we tell that the signal is quasi stationary. So, quasi stationary means that it is loosely stationary and the change is limited. So, if we take a small window, within that there is no change. So, we select such a window of time and limit the signal within the window, so that the assumption of stationarity is maintained. So, first job is to limit the signal within the window. Next, we go for Fourier transform, and we have taken the absolute value of it. Okay. And then we take the logarithm, and then it pass through the inverse Fourier transform, and for a efficient implementation of the Fourier transform and inverse Fourier transform, we have used the DFT and IDFT, and then that we get the spectrum. Now, the filtering, we have a different term for that, we call it is liftering. Again the term filtering is jumbled here, okay. It is called liftering. And the first thing to note here, that we have not done the phase unwrapping and we have not told it is the complex spectrum. The reason is that original signal was real. So, the complex spectrum also it would be real, and because it is real, that we do not bother about the phase or the phase unwrapping, okay. That we are not interested in that. So, we have just removed that and then go for the filtering in the septal domain, what is called the septal liftering, and we are separating the two parts. One side is the transfer function, which is a low frequency part. Okay. Why low frequency? Because the change in that vocal tract, it is slow. We cannot change it very quickly, and thereby that transfer function, it is a slowly changing, I would say that signal, and the other part, that is that excitation that is coming from the glottis, that is here a pulse of actually that impulses are coming from the glottis or glottal waves are coming, that is high frequency term, or here in this nomenclature we should say that high frequency part, and the transfer function is low frequency part. So, by that the general concept of filtering, by using the septal liftering, we could separate them out and we can actually find out that what is the transfer function, if we are interested in that. If we are interested in that to find out that what is the command that is given, then we may go for the glottal pulse, and here we see some example of it. Okay. To show the example that what we have done, first we have taken that male speech, okay, and two vowels are uttered, first is E, next is A for the male speech. Again for the same two vowels E and A, we have taken the female speech, and we are going to the that septal domain, okay, in all these cases. So, when we look at say for the E, for the male speaker, we get actually this is the septal coefficient, that y axis, it is giving the that septal domain, that here we get actually that this part is the the low occupancy part, that is given as the vocal tract, and this is the excitation, okay, that glottal pulse. And for the female speaker, we get this is the transfer function and this is the glottal pulse. Now, when we compare these two for the male speaker and that female speaker, for the same utterance, that the two the transfer function, they have some similarity, but more difference is there in the excitation part of it, and we see that more actually high frequency components are there for the female speaker. Okay. These components, that what we are getting, that at high frequency, that the parts are there, and that gives rise to the that fact, conforms to the fact that comparing the male speaker, the female voice is rich in high frequency component. Okay. And same thing we go actually and notice for that the other utterance are here also. If you look at the excitation part, that for the male speaker and the female speaker, we see that energy is more distributed to the high frequency part for the female speaker. Okay. And here by simple thresholding, that we can actually separate these two parts out, that is in the low frequency part we are getting that this part we are getting the transfer function, and the high frequency part we are getting the excitation signal. Okay. So, by septal liftering we can get that, and we can once more look at that the original actually that homomorphic deconvolution, that block diagram, that can help us to remember that what are the steps we have to take. And here one point just I would like to actually point it out, that as we are doing the filtering, that it becomes a simple actually a separation in this case, that becomes a very simple operation, and that way we could actually separate these two things out. Okay. So, and again after that filtering, then we need to take that Fourier transform, then the exponential transform and Fourier transform again to get back the time domain signal, whatever component maybe we are looking at, maybe the vocal tract or the glottal pulse, we can get that, but we need to actually perform the rest of the part which we have not shown in the previous diagram. Okay. So, that is how we can complete the process, and this is with this we actually complete the part of homomorphic processing. Thank you.